The only thing I really want to ask is just like, if anyone has anything they'd like to present, just please approach me after this meetup, and we just talk about maybe, scheduling that for the next meetup or some other meetup in the future. Otherwise, I'll probably end up giving the next presentation. And so I had the idea of maybe talking about asynchronous, using asynchronous libraries in Python, or maybe a presentation on Redis. So it's a key value store. It also has like a message, like a pub sub component to it. So it's commonly used for caching files. So anyways, with that, I'll turn it over to Craig here. So.
Our speaker today is a new dad. Congratulations.
Congratulations.
He just came back from New Orleans. His name is Aaron. And Aaron's primarily focused in his life on startups on data. And I asked him, what was your tipping point for programming? And he said, well, I used to play computer games like many of us. He got started on Nintendo, and then he wanted to get in, like everyone. I want to be a game developer, but he quickly realized how complicated that was going to be. But he did stick with computers, and so the computer he was using was a little slow, so he learned how to overclock and went ahead. And then got interested in doing hardware. And then he kept going, and then it didn't learn enough by overclocking it, and so he got a computer engineering degree as well as marketing. And after that, he worked in business data analysis, and he will tell you whatever you want to know about what they do with your little, I don't have my keys with me from the grocery store, but when you scan your data, they track all the things you purchase. He'll tell you things that you probably don't want to know about the data.
We've done most of those projects.
Yes.
He worked for a utility industry, looking at massive amounts of data coming from meters at 15-minute intervals for some power companies in Washington, D.C. And so he got very interested in what it is to do, what the industry term now is big data, but he's been doing data like that for a very long time. And currently he works for a company called videoblocks. Videoblocks is a subscription-based stock media company for artisans, and their catchphrase is creative content that everyone can afford. So if you're looking for something for your website or your videos, stock photos, whatever that is, he's the guy that works on, well, he's probably going to explain better than I will, but that's where he's working now, and he's currently living in Uray, and we're glad to have him. So tonight he's going to talk about database indexing, and he's going to basically talk about things that he wish he had known when he got started, but he's going to let us know tonight. So I'm going to turn it over to Aaron.
Thanks. I think I'll go ahead. I can just sit up there. Broadcasting wirelessly here. Does it screw up all the cameras and whatnot? All right.
No,
thanks for coming, guys.
Back and forth, dude.
All right, yeah. So real quick, work for videoblocks. They're a subscription-based stock media company. If you're looking for like a video of something to supplement, we also have graphics and images and whatnot. But I don't know, maybe an airplane or something. Videos and stuff you can use. And so the stock media space is pretty crowded. There's a lot of big players there that charge a lot of money. And so we're coming in, we're winning on price. But you're not going to get customers if people know you're there and they have a good time on your site. So there's kind of two big components to our success. is people finding us ranking high in search results, and them finding what they need quickly when they get to the site. And so that's where database speed comes in, is we found that even speeding up our page by 100 milliseconds will really boost our ranking in Google's and other websites' eyes, which translates to more customers, more money, and keeps me a job so I can feed that new child of mine. So if we look here at kind of like the way our web looks here, for part of our component, our view layer is still a PHP app. So you see our response time is around 150 milliseconds. Not the greatest, but it's all right. And this yellow, so this blue is PHP. Different people have different opinions on PHP. I have a very strong opinion on PHP, but I think this huge blue bar is kind of factors into that. It's a little slow, but still 100 milliseconds. Like it's not that slow. And then so then the database looks like right now on average we're at about 25 milliseconds, and then the browser has to do stuff and flip external. So by keeping this yellow bar small, we're able to get a lot of money. Yeah.
Sorry, what's that app that you're using?
This is New Relic. It's a great monitoring app and error logging tracking.
Okay.
They charge you per server, so if you just have one server, it's pretty cheap. Then it starts getting expensive
Okay.
as you grow. So we have other apps we monitor because we're breaking off our applications into microservices. Yeah, so here's another app. This is kind of a shameless plug for Node.js. So now we're closer to 10 millisecond and 25 millisecond, but still the database is a smaller component. So if this database jumps to take seconds or minutes, it's bad news for videoblocks. So it's important, and a lot of websites work that way too. And my old companies, we would have tasks that would take hours, but by efficiently using the database, if we weren't using it correctly, it would take days or just never complete. So there's like different kind of orders of magnitude of speed you care about, but since the demos I'm going to be giving I'm using a pretty small data set, and the differences are only in the fractions of a second. You might say, well, who cares if that takes.
What is
25.
small to you?
It's about 3 million rows.
As opposed to 10.
As opposed to billions, yeah.
I mean, like there's 10 rows.
Oh, yeah. And then, so why MySQL? So when you think big data, people often think of like Hadoop or Cassandra or a lot of these like huge, big, like typical big data stores. And all the companies I've worked at, right when we're considering like, oh man, should we really get Hadoop? Then computers would get faster, and we would just buy a bigger server and like problem solve. And it was a lot easier than. So we were actually able to scale up like pretty well, even into the billions of rows. So scaling out is one strategy to handle big data, and a lot of that strategy is good. Like we've used Hadoop and HBase at other companies and stuff, but like MySQL, SQL Server, like SQL-based languages can actually get to like reasonably large data sets. So as long as you index correctly. So that's kind of why this is important. So we'll go ahead and get started. This is Google Docs. Okay. All right. So why would you use indexes? So that's kind of the intro stuff. So okay. So how does MySQL store stuff? So MySQL has kind of swap-outable engines under the hood, but by default nowadays, and most people use InnoDB. So it stores your data on the disk, generally, and they kind of group tables together by default into kind of combine them into files to reduce the penalty of file system access. And the rows are just stored. So if you have and when I say a table, I mean like it could be like your name, your birthday, your favorite color. That's all going to be stored just in a file. And so the physical order that the data is stored in, that's how it's called. The term we use is like clustered. That's how it's clustered on the disk. But it would really stink to have to read that whole file every time. So what databases do is they index it. And what this is it's using often a structure called a B+ tree. And we'll just talk about B trees. B+ trees has extra bells and whistles. They can like balance themselves and whatnot. But basically, it's just a tree like this kind of shown here that then points to has pointers to where the data is on the disk. And so the way a B tree works is you have For each node, you kind of have like, I guess this one like the highest one. So if you're below 3, you know to go over here. If you're above 3 but below 6, you'll kind of go to this section. And if you're above 6 but below 9, you'll go over here. And if you're just above 9, you'll go over here. So you can kind of see how it uses. There's not always 3. Often there's more. But essentially you'll have like a couple of partitions, and then that will point to more partitions, and it goes and goes and goes until you get to the leaf nodes, and these have pointers to the data on the disk somewhere.
So this is specifically like indexing of integers.
Not necessarily.
I mean, just in this example.
Well, yeah, this example.
In this example, it was. I guess I didn't hear your question all the way.
The
But,
keys are in
Yeah.
integers.
they're integers.
oh yeah. So I'm using integers just to like make it simple. And often people will index like just some random, well, not random, but like an auto incrementing number. That's a common key. It's not always the best choice, as we'll see later.
So
But
how would you do this with scalars?
you can have compound indexes. You can have different types of indexes. You can index geospatially, but eventually, don't think of it as numbers. Think of it as things that are comparable. So if you can say
And
this
orderable.
is comparable and orderable. So if something is you can use it with dates, which are really just numbers on the hood. You can do it with text. So instead of like 369, it could be like A, M, and Q. So as it goes, it says like, am I less than this or greater than this? And it goes and goes.
Okay, I see. So like, it's just this would be.
Like there's tons of nodes. This is I guess
Something that'll fit on the slide.
this is an 11 record database. Yeah.
Pretending that everything has an integer key. Is that kind of the way that's
Yeah, everything at the end of the day will get converted back to
Okay,
to an
really?
integer.
Yeah, ultimately.
Kind of. But yeah, basically just have to know that it's like less than or greater than is like the if you can say this is less than that and this is greater than that, then you can put it into a tree.
By the way, this makes perfect sense. I was
Okay.
just curious. That's all.
It'll make more sense soon. Don't worry. All right. So indexing the data. So the best example I like to use is like an actual dictionary. So if I gave you a dictionary and said look up the word index, like how would you do it? You can talk. This is gonna be
the eyes.
interactive.
Basically, you put the thing in halfway and went there or not. Nope. Go back here, go forward.
Yeah.
Do a binary search.
I'd interpolate. I wouldn't do binary search.
Exactly. You kind of know where I is. You're like I is somewhere in like the front ish. So
that's
do an
just gotta be
interpolate.
really big,
But you-
and Q is only.
So you would take your best guess. Maybe you open it. You're at the M's on page 70, and you're like, all right, that's too far. Let's go earlier. Then you get to the G's on page 35, and you're like, whoops, I went too far early. So you're kind of like narrowing your range until you get to the page you need. So that's great. So that's kind of how indexes work. All right. And what if you just wanted to look up all the words that started with I? You would kind of do this. You'd go to the I's and you just start reading. You'd be like, okay, here they are. Now, what if you want to look up all the words that end in I?
Now you
Yeah, it's harder. in
That-
index.
Now you're in trouble. Yeah, and then you have to look at every single page, and that's where things get slow. It's called a table scan. So, okay, so we use this B tree, and so it's great. You were talking about like how to look things up. It's great for like single and range based lookups. Just anything that has like a equality or a greater than, less than. So questions like in this SQL syntax, like give me where's the number 5? Give me everything that's greater than 7, less than 5, between these. It's not good if you say, give me everything that's like not 8, because now it has to check everything. And so, so the way to think about it is like it's really easy to open up a dictionary and look for something that starts with the letter CH, like chair. But it'd be really hard to find words that have it in the middle. Look at everything. So, okay, so if you're doing the dictionary approach, it's gonna take essentially the log of the number of records you have in your database time. It's called log n. It's like kind of the big O notation there. And then if you have to look at every page, if you're looking for something that ends in CH or ends in I, that's just n. So the effort to find that will just scale linearly with the numbers. So here's like a graph of kind of how n looks with log n. And the reason you can't see log n move at all really is because it just increases so small. So if you have, I think this is 1 million records, if you have it indexed, you look at like about 6 things, and if it's not, you have to look at 1 million. So it really makes a huge difference, especially when you get to very large data sets. And even some, I know like MongoDB, if you try to run a query on a large data set that's not indexed, it'll actually yell at you and say like, I'm not even going to try this. This will take forever. I give up. So indexing is very important. Okay, so we're going to do something. So here's like just kind of how it will look. So if you're working through tree, if you're looking for where ID equals 5, you're going to look here. Is it less than 3? No. Is it less than 6? Yes. So you go here. Is it less than 4? No. Is it less than 5? Actually, you say less than or equal to. Is it less than or equal to 5? Yes. There's your data. You go retrieve your data. So that's great. It's easy. You only look at 2 nodes, and then you retrieve the record. Happy times. Where it's greater than 7. So usually it's not good to do this with like large data sets, but you might find yourself doing, even if you have a very large data set, you just want to get everything that happened yesterday. So you might just say, give me everything greater than a day ago. So you might just start doing a range scan. So one thing I kind of didn't highlight before is these nodes have pointers to the next one too. So it can, bidirectional. So once it gets where it needs to go, it can just start chugging along too. So it could actually skip intermediate layers that aren't shown here. So if you're like, where everything's greater than 7, is less than 3, no. Less than 6, no. Okay. Is less than 9, yes. So we go here. Okay, here's 7. It's that's not greater than, but 8. Okay, we'll get that data. 9. We'll just take the shortcut. 10, 11. So we only looked at the data we had to again. So this is a win. This is good. Less than 5, same thing, just on the other side of the tree. We're coming here. We get to the 5, less than that data. I guess I should have made this arrow bidirectional here, but then it would traverse here and go that way. So it's good. Between 6 and 8, we just start traversing, but now we have a stopping point, so that's great. When we get to the stopping point, we're done. So we're only looking at what we wanted to look at. Whereas now I go 8. Now this is bad. This is where we do, this is called a table scan. And that's where it just was like, I don't know what to do. I'm just going to start at the very beginning and just look at everything. And it knows to exclude this, but it still has to look at every single record. So this is you always want to be able to query so you get index. You can be kind of efficient like that instead of scanning like that. Also, if you look at something that's unindexed, it's an unindexed column. So maybe there's another in the data. There's more than just this number. So if there's no index for it, it just has to start at the beginning and look at every single item in the data set, which is set. Also, if you're applying a function to index column, you might think, oh, I'm using ID. So this is index, so I'm cool. Wrong. It's not. As soon as you apply a function to a column, MySQL doesn't know the output. Even if it's a deterministic function, MySQL is not smart in a lot of ways, and that's one of them. So it's gonna go. Now, it is smart enough to know that it could apply the function to the things in the index, so it'll only go to disk when it needs to, but it's still gonna have to look at every node. So this is bad. It's not as bad as this, but it's still decently bad. Although indexes are usually stored in memory, so this is actually a lot better than the full table scan. This is kind of like a full index scan. All right, so now we'll do a demo. And we'll jump in and out of demo land. There's a lovely testing data set people made available, open source. It's an employees table, and it's really easy. You just can bring it in with a command. So we're using it here. And it's going to be good. Actually, I'll go back to presenting this for a second. So what does this look like? So there's 2 relevant tables. One is employees. It has like an employee number. This is the primary key is what's clustered on. It's the only key. Then you have birthday, first name, last name, gender, and a hire date. Then we also have a table of salaries. Hopefully this doesn't get into the hands of the employees. And it has the employee number and the salary, and then like the from and to date, I guess when they were paid that salary to compensate for raises or demotions. There's no new, the key here is a clustered primary key, compound. So it's indexing on employee number first, and then from date is next. And it also has a foreign key back. I won't really talk too much about that. But the important thing here is employees. There's about 300,000 employees entered in here. and about 2.8 million salaries. So it's enough for us to have fun. And this is kind of like what the data looks like in not the console world. Great. Okay. So now we're going to have some fun with the queries here. So the first one is we're just looking up something using the index. So give me employee number. Give me all information on the employee number whose number is 20,000. So you can pull it up in 0.00 seconds. It's rounding down. It took some time. It wasn't instantaneous,
How
but
many records did you say were in there?
300,000. So it's not. And this laptop is not very fast,
It's a MacBook Air.
which is good. It's a MacBook. I would not recommend it, just so you know. I'm an early adopter, and I love the MacBook Air, but I did not like this. And the database is running in a container on Docker. And Docker for Mac uses a virtual machine, so it's like slow, but it's like should be a little slower, which is good for us right now. All right, so if you look at this person, the names I think were kind of randomly generated here, but we have Jenwei Matsky. So what if we tried to find them by that later instead of using the key, instead of using what's indexed?
So since there's a primary key, there's an index on the primary key by default.
Yeah, index is on the primary key by default. So it can just log in time, find it. Now here, there's no index on last name or first name, so it's going to have to scan every record. So it took 0.9 seconds. You might be thinking like, oh, that's fine, like whatever. But still, that's 90 milliseconds, which would be more than half of the entire transaction time of our average request. And we hit the database probably 50 times per call to our website. So this is like a long time to find this. So you can see the effect it has. And even if you're doing aggregations, so if we want to find the min and max, this is now in the salaries table. If we want to find like the smallest and largest employee number, it's like instantaneous basically because it's right there in the index. But now we want to find the smallest and largest salary. So it really had to think about that one.
Yeah.
So because it had to look at every
Had to look at 2 fields in every record.
every field. So this is, probably at least 100 times slower. So if I look for the range, if I want to know how many employees do I have between 20,000 and 25, probably 500. So it's close. So we have some missing employee numbers, but that ran pretty quickly, 0.02 seconds. And then if we want to find, okay, well, who's making between 70 and 75,000, took 25 times longer. And so it takes a while there. This would be disastrous if a query took 600 milliseconds on our website. Google would say, your site is way too slow.
Remember
Everyone go.
Yes, we do.
Yeah.
I remember 50 baud. You could watch the bits go by.
Yeah. So and that's this isn't the time it takes for the browser to render. This is Google's also measuring just like when even just when the first response header is sent. But yeah, I think I know is a relatively new problem, but unfortunately it's the lifeblood of a lot of new companies because it's how they get discovered. Okay, and when I distribute this presentation, you can see if you highlight over it, the spoilers are there. You just have to mouse over. So, all right, so that was our demo. There'll be more demos, don't worry. But okay, great. So indexes are awesome. So why don't we just index every column call it a day? It's great.
How much disk space do you have?
And all right, so basically,
You've been talking to me?
what you'll be doing is creating a spread out copy of your table that's wasting space and memory. And you'll really slow down writes because every time you add to the database, it has to rebalance the index. And so if you create 4 indexes, then every time you insert, you're going to have to update 4 indexes. So now your database kind of looks like this with a bunch of different indexes. This is like a very small database of small aircraft. And actually, in reality, it's even more complicated than this because secondary indexes, leaf nodes, point to the primary key, which then points to the data. So there's like an extra spider web on top of this. So it's not a good idea to index all your columns because you'll really slow down writes. And
But, so is this mostly a space issue though? Because you said indexes are in memory, which is a lot faster than.
the indexes will be pulled into memory. Yeah, so there might be some, if you're only reading, there might be an argument to index every column if you really are.
If you had that much.
But chances are there you probably wanted things stored in like different tables or
Yeah, the main problem is updating the updated record. You have to update every index.
yeah, writes and deletes.
But if it's in RAM, it's going to be.
Well, yeah, but if you want it persisted out the disk, then you have the disk.
So you have a copy of the index
Yeah.
in memory, but the
The
it has
database
to
pulls
store
the
on
index
disk
into
or
memory
something.
to operate, but a lot of times it won't.
So for every
it
query,
usually-
you have to rewrite the index.
every query has it'll have to
Right.
every
Okay,
insert
right, right,
yeah
right.
every insert or deletion or update will have to rebuild the index.
Okay.
And usually the database doesn't have enough RAM to store every index in memory all the time. So it's like storing a disk. So it's just complicating. Yeah, it's just complicating the situation. All right. So, but what you can do is if you want to do, you can do compound indexes though. So these are common. So if you have 10 columns, you might want to index kind of 3 of them in order. And this is basically to handle, I think, scalars like or vectors. What was your question again? How do you handle like 2-dimensional data? Or yeah. So here, if we have numbers and letters, basically it's just going to compare the first and then the second. So one thing to know about compound indexes is you're getting everything to the left as well. So if we create a compound index on number and letter, we're getting an index just on number for free. Like even if we're not using the letter part, it can use number. So good, if we could query where number equals 4, or where number equals 5 and the letter is less than C, those are good queries. If we're only using the right part, that's not helpful, and you'll see that soon. You need to kind of use everything here. So if you're saying where number equals 4, we go, all right, is it less than 3? No. Is it less than or equal to 4? Yes. We go down here. Is it less than or equal to 3? Is 4 less than or equal to 4? Or is 4 equal to 4? Yes. Pull that data. And here we'll pull that data too. And then we go over here, it's 5, and we're done. It's actually, this should be orange because it would need to at least check this one. But so it's efficient there. And then when you say, when you're adding the number, the letter component, it's nice here because you can say, give me everything that has the number 5 and a letter less than C. So it goes over here, it gets the 5 realm, and then it can keep on going from there. The 5s, the A's, and the B's here. So that's great. But if you say, only give me things where it's C, it can't, because it's not sorted just on letters. So it has to look at it has to do an index scan. It has to look everywhere. And start at the very beginning until it sees things with C and then pull those records. So compound indexes are only useful when you're going from left to right. So if the only data you need is in the index, so let's say I only want to get the letters for everything that has a number 5. This is known as a covering index and never has to go to disk. So this is very fast. So typically, like join tables will be this way, because it'll just have like a primary key that's the 2 tables it's joining. It's other things. So it's great. So if you're saying give me everything where the letter or where the number's 5, give me all the letters. It's gonna look at the index and say okay, A and B. That's all. It has all the information it needs to know right there in the index. So that's good. Okay, so why not just use a compound index to cover your whole table then, if that's good? Because then basically what you're doing is just recreating a more complicated version of your table again, and it probably won't fit into memory, so you're losing that benefit of the index, and it'll still have to go to disk. So it's you're not gonna if you create a compound index of your whole table, you're not really gaining that much. And everything has an exception. So there's always like everything I say is not hard and fast. There are situations where you might want to create a covering index of your entire table. Like if you're always querying by these first 3 and sorting by the last, there's situations. But okay, so we'll go into a demo now to just illustrate the beauty of compound indexes. So if you remember the salaries table, basically it has an index on, or we can show it here. So we have an index on employee number and from date. So from date is the right part of this. So here's a query where we're only querying the right side. It took a long time, 0.82. So, and before we were doing like the queries that were selecting the max employee number, those were fast. So this is much slower than when we were doing like this query right here, which ran like rounded down to 0 seconds. So even though this table has an index that has a from date in it, it can't use that index. So it has to do a full table scan because we're only asking about the. Actually, here I asked, give me the maximum to date where the from date is between these two. So now, so now we'll create an index on from date. It takes like 6 seconds. Let's see. There we go. Okay. So now we have our index. So now I want to select the max to date.
Same query.
Same query. Same exact query. It's fast.
Fast.
0.07 seconds.
Index.
So this is the maximum date. So that's great. All right, we'll go ahead and drop that index now. Okay. So now what I'm going to do is create compound index that is indexing both the from date and the to date. I kind of went off the screen there. Okay, and in MySQL you actually tell it to index descending or ascending. It doesn't make that much of a difference because there's bidirectional pointers, but it can like if you're trying to squeeze every millisecond out, you can like optimize the sort for what you're expecting here. And so since we're selecting the maximum to date, we're saying I want you to start the index at the highest to date here. So I'm going to create that index. That's great. So now we're going to rerun that query. And what this query is doing is it's first is narrowing down everything down between these dates, and then it wants to find the highest to date in there. And so that is now 7 times faster. Because to date is now in that, it's covered by that index. And so it didn't even have to go to disk to pull that to date to get the highest one. So it's a lot faster. So that's good. So 70 milliseconds would be kind of annoying to add to our website, but 10 milliseconds we can stomach that. All right. All right. So clustering. This is where my company its employees probably screwed up the most. We're still working on this. And so clustering, you only have one clustered index because that's the order data is stored physically on the disk. And it's great because if you're retrieving things sequentially, it's a lot faster. Now this mattered a lot more back when we had magnetic disks because I had to spin the head to the right section. But even with solid state disks, where it's kind of like a conceptual grid and it's pulling down blocks at a time, it's still, if it can pull everything in one block, it's faster. Right. So it's still important, but it was very important for magnetic disks. But it's still very important. So like a solid state drive, if we say we need to pull this data, like these might all be located in the same block, and it can just pull it all at once. Okay, so what we're going to do is we're going to create a clustered table, a table that has a bad cluster. So MySQL, it's kind of annoying. It only lets you cluster on the primary key. Other databases let you define a clustered key. So what people do, especially employees at my company, is they always add an ID column to every table they create because they probably read that in a book and they just assume that every table needs an ID column. And so every table always has an automatic ID column, even if you don't need it. Like salaries, we'll never refer to a row in the salary table by itself. We're always going to refer to it in the context of like an employee number and some dates. So this ID is not needed. But what we're going to do is we're going to create a copy of the salaries table. We'll call it salaries unclustered. It's going to be exactly the same except it has this ID here. And we're just going to copy the data from salaries, but randomize the order. So we'll go ahead and run this real quick. Okay. then this will take
Take a little bit.
I think like 45 seconds or so. So what it's going to do, it's going to create a table that looks like this, where now sequential IDs have like different employee numbers. And so here's the dates for this employee, and then this employee next shows up at ID 300,000. So it's, because it's clustered on ID and it's not clustered on employee number, all the salary entries for a single ID are spread out around the disk.
Twice.
You don't get locality of reference.
This is what your employees were doing.
A lot of our tables are still this way because it's kind of a pain to
Okay.
switch. Yeah,
You don't,
they were just
you don't
just
want to be the auto, the dictator DBA that goes, I'm just going to rearrange your tables for you.
yeah. I know. I've done that a few times. I've just rearranged troublesome tables. Okay, so this is what the table looks like. So now we're going to go ahead and compare clustered to unclustered performance. And it really matters with large, like when you're pulling a lot of data, because that's when clustering helps. So we want to select a bunch of information. Can you guys see these queries okay? I think?
Yeah.
Okay. So we want to select a bunch of information on employees, about 1,000 employees between certain numbers. So we got it in 0.04 seconds, so that's great. And so now we'll select the same thing from the unclustered table. Oops.
So you can get the rest of the query.
Yeah, do not get the rest of the query. 0.8 seconds, so it took twice as long. And this gets worse the more data you're pulling. And so twice as long is bad. Okay, but it's even worse when you're trying to update because writes are harder for hard disks to do than reads. So if we're updating, let's say we want to double everyone's pay. This is great.
The Christmas bonus.
Christmas bonus for these. So on the cluster table, it worked in 0.9 seconds, and then on the unclustered table, uh, 0.11. So it's slower there as well.
By this time, you probably pulled everything into RAM buffers.
And yeah, it might be, because these are slowed up, it might be, the whole entire database is 150 megabytes, and we have 8 gigabytes of RAM here. So it's,
I think you're
but
good.
the important thing is just to know that it's like
Yeah.
kind of the orders of magnitude. Like this is still 30%
Yeah.
slower, that's slow,
Yeah.
and it actually gets a lot worse with larger data. As we say, just kidding. We're not going to give everyone a bonus.
Darn.
So 0.6 to reduce
The money
it.
goes away faster than it comes in.
Yeah, it does.
Funny how that works.
Yeah, and 12, so it's twice as slow. So we're seeing, in this particular example, it's twice as slow, but with larger data, it gets even worse. So the actual physical, ideally you want to, for the most common, like multiple read scenario, is how you want to cluster your data. Okay. I know I'm going kind of fast here, trying to make that hour. Any questions so far? Okay. All right. So now I'm just to throw in. That's like the main. Those are like the main key components of indexes and how they work. You can have single, you can compound, you can cluster. So now I'm just going to throw a whole bunch of like kind of open the doors. Some rules on how our index is used. Well, they're used when you select. They're used when you group stuff. If you're trying to group.
Order by.
And they're used to order. Yeah, to sort. They also are used when you're joining. So if you have one table and you're trying to look up, combine a column to another, it's going to use it. It's not going to scan the table for every row, because that would just be crazy. If you're joining 100 rows to another table, you don't want to do 100 table scans. You want to, for each one, you want to know exactly where to go to join. Indexes are only useful when the entries are different. So if every row in the database, the first name is Aaron, and you create an index, it's not going to improve anything. It's not going to speed it up.
There are cases where it does, but they're not normal.
There are atypical cases. You could do it if you have sparse indexes. So if you have a lot of data that's maybe you have like a bit and it's mostly 0 and there's like a couple ones, you can add an index there to like quickly find the ones that are ones. If you have a bunch of data and most of it's like null, it's not even populated. So there's things called sparse indexes. I don't think MySQL supports that. There are things called partial indexes where you can restrict an index to a where clause and say, I only want to index employees that started after October, but I want to index the first name. And then the query, the database will see, oh, you're asking about employees after October, so I can use this index to help with the name. But if you're asking for before, I can't. So there's other indexes. MySQL doesn't have that. But in general, indexes only really help when it's very unique data, like a key or a number or a date. For compound indexes, you want as you're going from left to right, you usually want to start with how you're going to narrow the data down, the where clause, and then the last one or last columns will be how you order it. So if you're selecting employees who have the first name Aaron, you want to order by the start date, you're going to want the index to be first name, start date. Because if you have start date, first name, it's not going to help find. It's going to have to look at every single table there. It's usually better to extend an existing index than to create a new one, and that's because each write has to rebuild the index. So if you extend an index, it only has to rebuild one index when you write. Whereas if you
by that you mean turn a simple index into a composite index?
if you can.
Okay.
And what I see a lot of my employees do is they'll be like an index on like employee number, and they think, oh yeah, well actually I'm gonna look up by employee number or employee number, bad name, the index on last name, and then I'm gonna sort by start date. And there's already an index on last name, but they're like, oh, that doesn't help with sorting, so I'm gonna create an index on last name and start date, and then they leave that other index there. And MySQL isn't smart enough to know, like, oh, this index is now useless. So when you extend, you want to make sure you drop the old indexes. And so indexes work better on smaller columns because ideally the whole index fits into memory. So like integers and dates are good. Dates are basically just numbers under the hood, number of seconds or milliseconds since an epoch. Yep. Yeah.
I have a question about what you just said.
Yeah, sure. This is like the fast. This is where we go fast. These
No, it's
slides.
fine. So
You ask
make a
questions.
composite index,
Uh-huh.
but you didn't extend it. You just created a new one, and you're left with two of them now.
Yeah, MySQL doesn't let you extend indexes. You actually have to create
Okay,
a new one. Yeah.
there's two indexes in there.
Yeah.
Now, let's say that somebody created one on employee number, and then like the employee number and start date.
Mm-hmm.
And you say once you have this composite one, delete this one. If you run the queries, do you still get the optimization if you're using a composite index, even though you're only doing sorts on one aspect of the composite index?
The composite index is conceptually an index of everything going left to right. So if you have a composite index on A, B, and C, then you also have an index on A and an index on A and B.
Perfect. All right.
Yeah.
No, but then the index is larger, so if you had memory constraint problems, it could be a trade-off.
Yeah, there could be a trade-off. Yeah. So that, everything has exceptions. So if your index gets too large, then it's not going to be useful. You're going to hit a tipping point. So two indexes. Yeah, everything here is like, these are just rules of thumb.
Usually.
I put this here. This could be a whole presentation because it's true. Okay, so indexing dates is good. Floats, that gets a little more complicated. That's not terrible, but they're usually a little more complicated than integers. And then this is what happens at my company a lot: is just large character columns.
Text fields.
They'll index, email addresses. They'll index. We generate like 128 hexadecimal unique identifier for users, and then they'll just index the entire thing. So if you have 128 characters, each one, I think MySQL stores 2 bytes per character with its data set.
UTF-16?
Because I think it's using like a Latin correlation. But yeah, essentially UTF-16. So you're looking at 256 bytes times 40 million rows. It starts really adding up. So we'll do a demo here on, this is my favorite thing to do. And this is, if you have something, what you can do is you can run tests. If you have a large text field, how do you know, how you can index a subset of the characters? And one way to do this is just to actually see how selective the number of characters are. So now this data was randomly generated, and they use a lot of repeats. So this is kind of atypical results. But basically, if we index just one character, it's 0.01% selective. So that's not good. If we index 2, now it's 7 times as selective. Keeps getting more selective, but now it kind of asymptotes here. And the most selective we could possibly get is 0.5%.
Right.
Typically you'll see information like it'll look closer to like 0.9.
What's it measuring?
This is measuring how the cardinality of the index basically, or how selective, like how much it narrows it down.
Yeah, no, you answered.
Yeah, so if you were to index the field completely, it would narrow it down to like chunks of 1 like 200th, I guess.
It's really cool.
So
you're basically saying that like you're only indexing part of a field.
Right.
Right?
what this suggests is you could achieve 100% of the effective indexing all 16 characters with indexing just 9. And you could achieve most of the benefit by indexing just 5.
Yeah, this is a way of avoiding guesswork and actually getting the hard number. It's like
Yeah, I wouldn't guess. And if your data is growing, I would add a buffer. So like looking at this, I'd probably index six characters instead of 5.
That's cool.
Yeah, so we'll do a demo here. So employees, the last name, we do select. Actually, we'll get the maximum length too.
Is it a comma or period?
That's a comma.
Okay.
Yeah. All right. So even though we have 300,000 employees, we only have 16,000 last names. So if we, and this is like I think this is just a factor of being randomly generated. So if we look here, yeah, the most selective we can get is about 0.5%. Normally this will look like 0.98 or something like that is how selective you can get. So this is just a downside of using this data set here. But that's okay. So all right, so for MySQL, whenever you're going to look at index statistics, you want to run analyze table. Different databases have different commands to like update their table statistics. SQL servers update table statistics. But if you just Google like how do I update my table statistics, there's a command for it. So you can run that. So now we can query kind of the database internals and see. Did
you actually create?
I didn't create the index. Yeah. Skip that step. All right, there we go. We create the index. Let's see if up works. There we go. So we reanalyze the table, and if we look at that, so that index is 417 bytes. I'm actually not sure what the unit is. There. I probably should know that, but I don't. I think it's bytes. I'm pretty sure it's bytes. So that's the index size there. It's probably doing some compression and stuff under the hood. But all right, so let's go ahead and just index the last 5 characters.
You mean the first 5?
Sorry, the first 5. The first 5. Yeah, the last 5 would. It doesn't even let you do that because it doesn't make any sense.
Yeah.
So this 5 means the first 5. Yeah, and now we'll look at the next one. And so we saved a lot of room there. And generally, how much you save is like related to how many letters you're cutting off versus how big the data is. So it's on a 300,000 row table, you're not gaining a whole lot. In fact, we looked at it for 8 million row table today. We had an index on a field that averaged 14 characters, and it got unique around the 9 or 10 or 11 character mark. That's only really going to save us about 50 megabytes or something like that. So it wasn't worth doing. But there's been other situations where we have character fields that are hundreds of letters long, and people just index the whole thing. And then we only needed the first 10 letters. So this is handy. This is like a handy trick to effectively index text fields that show up a bunch.
Is this kind of a known approach to do index fields?
It's a known indexing strategy. Yeah, that's why they let you index just the first few letters.
Okay.
As far as to find the selectivity, like this,
Yeah.
this is probably not as well known as it should be, but you could just guess. I don't like guessing, so
Okay.
Measure.
yeah. If you do this though, if you're doing this on production data, do set it to like not make it a non-blocking read, because usually this takes a long time. So if you're doing MySQL, you would do set transaction isolation level read uncommitted. Other databases have different options, but just don't actually screw up your production app when you're. This is a long query.
Run this on Friday night, not Monday morning.
Yeah, exactly. All right, so some other things about indexes, just kind of zoom along, is MySQL has implicit indexes. So the primary key is automatically indexed. If you don't have a primary key, it's going to just make one up for you behind the scenes indexes. So you might as well make one. There's no benefit to not having one. I think you asked earlier, you were a little bit ahead of it. The left part of the compound indexes can be used. So if you can use left. All secondary indexes really just point back to the primary key, because that then points to the record. So the secondary indexes don't actually point to where it is on disk. It just points to the primary key. That way, if things are repaged and moved on disk, only one index has to be updated. MySQL and a lot of other databases will, if you make a foreign key, will automatically create an index, just because it'd be very difficult to enforce. So, and then if you create a unique key, it's going to make an index as well, because otherwise it would be very computationally expensive to check if something's unique. So if you run create table, it's essentially going to create an index on ID. If you create this compound index here, really what you're making is an index looks like this, and an index looks like that. If you have a foreign key, you're going to get an index on it. And it'll create an index on the other table, too. And then if you make a unique key, let's say you make this, you say you want make, model, and name to be unique, then you're actually getting all of these indexes. All three of these are going to be created. So something to know. And so a lot of times people will create like a unique key, and they maybe have like this index from before, or that one. I think MySQL is smart enough to, if it created this, it will drop it if it realizes there's another index it can use. But if you made this index, you'd want to drop it. Because if you make this index now, this one's not needed anymore, because it's fully covered by this index. Actually, no, it's not. Sorry, it's a bad example. This index is fully covered by this index.
Yeah.
So if you made this index, and then you make this one, you'd want to drop this index. All right, so here's some like kind of examples. I'm making a table called people as an auto-incrementing primary key. We got a first name, a middle name, a last name, age, and gender, and like a date joined. So some good indexes would be age. This would be good if I'm running queries like this. If I'm looking for age and sorting by date joined, then this is a great index, because it's going to use the age part to filter it down, and then it will just use the secondary part to order the results. Same if I just want to find the maximum. For last name, maybe I determine 4 is all I really need. So it'll be good to query by last name, or even just by the first few letters. So if I want to find everyone whose last name starts with Q, that's good. So what would be bad? If I create a unique index on first name and last name, that is going to be it could possibly be a 50-byte index like that. This I see a lot. So there's sometimes ways to get around this. Just be careful indexing, especially compound indexing large text fields. And then if you're running queries like this, it's going to have to table scan. If you're selecting last name, even if it was indexed correctly, if you're this like means it ends in SON. So ending, it's like looking up the dictionary. It's going to have to look at every table, so that's not good.
Yeah.
And then here's like first name from people where the age is like a multiple of 10. Basically, the mod of it in 10 is 0. That it's a function, so it's going to have to do table scan. So some kind of just Just some examples here. All right, so this is a real table from our company that I stumbled upon because it was causing a lot of trouble. And if you look at it here, who can point out some things wrong with this table now that we've learned all about indexes?
One of the very first things is
You
you
just-
mentioned, if you're really going to be looking at things probably by member ID, you probably don't need an ID field.
Yeah,
You just
there's
member ID.
never a time I'm going to say, just give me this change.
Yeah.
It's usually going to be, this is a table that tracks when members change from one plan to another.
Okay.
And so we're always going to probably have a member ID if we're looking up. So the ID is not needed. That's one example.
Although I've always heard you don't want to use anything with logic as your unique ID, because as soon as you merge two companies, you want to keep the old member IDs. You suddenly have a problem.
Yeah, but you could always add IDs after the fact.
Then you can-
we did that with the unclustered table example. So,
Yeah.
but yeah. So in that case, typically what would happen is they would append a company ID number. So then you'd have a composite index of company ID and member ID. And we're actually doing this right now because we have 3 different sites and we're combining them into one. So, okay, what else is wrong with this table?
Too many keys.
Too many keys. Which keys can we just get rid of right off the bat?
Let's see. I don't know.
Anything that's not a foreign key.
You get rid of the last one. Old date plan.
Old plan. Yeah, we probably don't need that plan. So here, if you look at date added, it's fully covered here.
Here.
And the key is actually even called date. This is MySQL being very
Yeah.
condescending.
Yeah.
Well, I noticed that also you have the thing new status and old status is covered by new status, new plan ID, old status.
Yeah, and this is strange too because it's, well, you can't tell here, but there's not that many statuses, so the cardinality is, this should be enum too.
Yeah.
Yeah.
But I gave this presentation or like a subset of this presentation to my company, so some of it is, you do need some context. And like the statuses, it's like active, canceled.
It should be an enum,
It should be enum, yeah.
Yeah.
Okay, so we also have an index here on new subscription date and old subscription end date. It's and it's just that's the new subscription. Like, so one thing to know about dates when they're being inserted into the database is they're almost always going to be like pretty unique, unless people do something the exact same millisecond. So if we're arranging things by one date, and then we're trying to further subdivide it by another date, we're probably not going to do anything. It's probably just going to subdivide. It's not going to do anything because you can't subdivide
I
one.
mean, the only thing I can find out is if you just did a select on old subscription end date by picking on new subscription end date as your key, so you don't have to hit the record. But that's the only thing it buys you.
It's the only thing that would buy you. Yeah,
But I don't
and
know why
but that's not a good reason to have this key.
Yeah.
So there are a lot of things wrong. So I only looked at the indexes here, but you're right, ID's not even needed. But basically we have 10 indexes and 18 columns indexed, 18 index columns here. And then date added is unnecessary. It's highly unlikely that the old status is needed, like you were saying. It's also not a very useful index. Highly, whoops. Yeah, so, and then, if you have a lot of indexes or here's a weird situation where like the two
The
are
same thing, but in
the
reverse.
opposite, and like chances are we're only using one of them by querying. So if you ever see that, it's kind of a red flag. So it's good. All right, so now you have all your indexes. Like, what are some rules to like write queries to take advantage of them? Real quick, is first of all, create the indexes based on knowing how to equate a table. And if you don't know, make it your best guess. But don't just add indexes just in case. It's really easy when you start seeing a spike in times. My databases have like slow query logs and other mechanisms to figure out if you're not indexed well, or your site will crash.
Does MySQL have a command that shows you how the query planner
Yeah,
uses
we'll do that
indexes?
next. Yeah.
Okay.
So all right, so if you write a query and it needs, you're like, I need a new index. Maybe you can rewrite it so it doesn't. So if you I'm trying to think of a good example here where There's ways you could kind of rewrite the query to like use other indexes just to help narrow down the data. So if you're looking, maybe you're trying to look for any records that have been like updated. Let's say you have employees. You're trying to look for any employees whose salary has changed after a certain date, and you know when that employee was terminated, and that column might be indexed. You might be able to say, give me all the employees that were like haven't been terminated yet, or termination date is greater than this, and then look for the salary change. And then MySQL will use that index to narrow the data set enough that you don't really need it indexed for the column you care about.
This goes along with what Kim was saying though. I mean, there's an optimizer, right? So
Yeah,
it's
and you can see how
your query anyway.
Yeah, but it'll tell you, a query planner will tell you what indexes it uses and what fields it's going to access. At least that's the way Postgres works.
Yeah, Postgres is very similar, just more intelligent than MySQL.
Yeah.
Okay, so I would see.
But you could add, you might have to add things to the database. The query optimizer will optimize with everything you give it, but sometimes you might be able to adjust your query in such a way that it can open up new indices.
So
In
it's
a
not
multiple,
perfect, is what
in a
you're
multiple
telling me.
where clause, you want your first condition to restrict your set
The most.
the most, because the subsequent things have a smaller data set.
Yeah.
So it's your knowledge of
Your
greater
knowledge. And the order of the where clause, the actual order on the screen of the where clause, the optimizer doesn't care about, but as long as there's something you can use, it will pick it out. Yeah. Okay, so if you need speed, then you can use cover indexes. This actually has nothing to do with indexes. It's just like a heads up. If you store like large for MySQL 768 characters, it's going to be stored off table. So that's
So he's using 1K.
it's going to have to go to the disk. Avoid nested subqueries, because that I just fixed a bug with this lately. It really throws the query optimizer off. You think it'd be smart, but it wouldn't.
But they're wonderful test questions.
They're good.
I'm a teacher.
Avoid your functions on the index columns. I should have said that. In like your where and your group by, your having by, and your order by. So you don't want to do order by month. And I actually had an example of this. Maybe it's there. I'll come back. But functions take a really long time. I'm pretty sure I had an example of that. Let me see.
Wasn't it in one of your first examples?
Yeah. Did we do it? Maybe we did do it.
Where you had a function in the where clause?
Yeah.
Yeah.
Okay, great. So if you're using temporary tables, which MySQL will create with subqueries, or if you're unioning, it's going to create a temporary table to combine all the results. If the result set is large, it's going to throw its hands up in the air and go to disk. And so if you are selecting using an index, a lot of data, and then you're maybe unioning like a very small amount of data, also using the index, it might still say, oh, I'm unioning and I have a lot of data, I'm going to disk. And that can slow you down. So there's just kind of something here. Okay, and if you're stuck, you can always run analyze table and then use explain to dive in. So that's what you guys were asking about. So here are some queries that we can look at the explanation for. And I think I'm actually going to use it in this other program, which is, I find it an easier, this is like a kind of an easier way to interface with MySQL. Although, I don't know how to boost the font.
That's all right, we're used to 7 point.
Usually if you hold down command and scroll or hit plus, it works, but it's just...
Can anyone not read that?
Well, it's going to come out the... We can try here and just maybe change it. Okay, so I want to find all my employees whose last name starts with A. And let's try again like this. Yeah, this is not. Let me do it here. Oops. Okay, how well can you see the?
Yeah, we can see that.
Let's make that out.
It's pretty small, but it will say like I'm going to use this index. It's one we created. The last name, first 5, actually. It says it there. It has its guess on the number of rows, and then the amount of rows that will like filter down to. So great. All right, it's using index. It's good. Good times. I want to find all the employees whose last name ends with A. All right, possible keys. These are the indexes it's considering. None. There's no key. It's it's not gonna be happy. All right, what if you have multiple tables involved? So we want to take their employees and join. So I want to basically get the salaries of all the employees whose name starts with A. All right, so you can see kind of like on the first, it's going to use the index employees, then it's joining, and there it's going to use the primary key, because the primary key is employee number on the salaries table. So that's great. That's really good when it's using primary. This is great. So it has a bunch of different keys it's considering here. It has the full employee name, last. It actually did consider the primary key because we are joining on employee number, but it didn't pick that one. There we go. It's good. So that's great. All right, so now what if we want to find all the employees or whose name starts with A, and we want to get the salaries basically like within the first 3 months. So now, once it goes to the second table, it doesn't have a key it's going to use. So sometimes you can use keys on some tables, and I think what MySQL is thinking is by the time it's joining, it's going to use the key to join, but it's not going to use any keys then to further like filter the. Actually, no, it can't use that key to join because we're joining using a function here.
Yeah.
So, this is actually kind of an absurd query here because it's going to give you all salaries, not just for that employee.
Oops.
So that's why it's weird. So it's like, so it will run it, and what we'll do is it will create like a nested lookup. That's where we'll create the hash table in the background to use. And you can even see over here in this like extra, it says like it's going to do a range check for each record. So that's like that's not nice. Or just an extra note. So explain is like a whole like another topic, but. Basically, you can look at the keys. If it's not using keys, that's like probably the source of your problem. And you can use explain to like really figure out what the query is thinking. And sometimes some databases allow hinting too. So if it's looking at possible keys and it's choosing one that you know is a bad key, you can actually hint to it in your query and say like, I want you to run this query and use this index. And it's just a suggestion. So the database might ignore it, but usually it'll listen to it.
So could you, in the on portion of that query, could you add last name like so-and-so at the end? And then you would... Yeah,
for inner joins, it's kind of, you can put it here too.
But you'd want that to execute first so it limits the, right?
Well, it's not going to... This will execute first, probably.
Okay. So it doesn't have to do with the order. So
no, the query and the join, the order of the from, and the order the tables appear, and the order of the clauses, and the joins and the where appears. That's the query optimizer will change that all around depending on what it wants to do. So it's usually you write it in the way that makes like the most sense as a human. You're like, I'm going to start with employees, and I'm going to get the salaries.
So the query optimizer would see like that function call. It's like, let's put that last.
Yeah, if I say like give me
so
every,
it knows that no matter what, it's going to do a scan.
If I say join employee number, so this is what we want to do.
Yeah.
If I want to find if I want to get the information on the employees for everyone who's making more than
me,
let's say like 50,000, even though I have employees first. The it's gonna start from salaries because that's like what's gonna restrict it, and then join back to employees.
Oh, I see.
So is this just kind of a weirdly constructed query to illustrate what's
Yeah,
not?
yeah, it's just a weirdly
okay.
constructed.
Because wouldn't you normally just use an and rather than
Yeah, you would use.
Okay.
You would, yeah. These are just kind of silly examples.
Yeah, I know it's unrelated.
Yeah, but yeah, no, the order. Like if someone's like, "Oh, your query's not fast," and they just rearrange the order you join, that's doing nothing. Or if they rearrange the where clauses, that's doing nothing too. So yeah, so you can use explain. It's a cool tool.
These are real queries that he found in his optimization of his employees.
Yeah, all right. That's it. That's hopefully you now know how indexes work and how to make more efficient indexes. Because at the end of the day, you're trying to keep your times low so your customers are happy and the search engines are happy, and you're making money.
So how do you start? Say they hired you, like they did, right? The performance is, man, it shows up. They bring you in, and you start poking around. How do you look at the code first?
Yeah, so databases have slow query logs.
For selects. So what do you know?
Theirs looks like something happened. So you can go. Now there's like very sophisticated tools where I can look at the like the biggest offenders here. So here are the most time-consuming database hits. So
3.5
we have something
seconds.
taking 3.5 seconds.
And just to know, this is extremely simple to set up. Like this is just like
Yeah, you just drop like a couple
it's
lines
like
of
plugin.
code
Yeah.
on
So
your
what's it
server.
called again?
This is called New Relic.
Yeah, we use this
But this,
extensively. And it's
does this point to where? What is the field that's in that you're clicking on? Is that?
Oh, this is just I guess monitoring a bunch of stuff here, and it's this one's not.
But
as
those
interesting.
aren't MySQL functions
They are. They're select statements that it's
that somebody wrote. Those are select statements that somebody wrote.
these are this is like it's the kind of at least the table that they're selecting from. But you can find so like here are the example actual queries. So someone
Oh, okay.
someone wrote this query
Okay.
here
so yeah.
Got
that is taking a long time.
So the plugin understands MySQL, and it'll automatically just send this stuff to New Relic. Same thing like on the front end, for example, you can add like you kind of like Google Analytics. You just import it, right? And it
I wish I invented New Relic. They're making a lot of money right now because they made it really easy for people who don't know much to set up very sophisticated monitoring. And they can even have alerts sent if your sites get too slow or
that's what the word
servers get.
So you click on that, you see it 7 seconds. It takes you exactly to this.
Yeah, so you click on.
It shows you where in the code that it exists as well.
Yeah. Yep.
Okay.
And where
And
the
it tells you which person submitted that in the GitHub.
Look at
Yeah, then you could do git blame, and then you could say
Does it generate the pink slip?
no.
Yeah, you can do like
We're tolerant of mistakes at my company, but we just use them as learning moments.
So if you're monitoring like an API, for example, it'll tell you what version of that API. The endpoint call was like if you have multiple versions out there in the wild, and you can compare like you just deploy a new version of some API. You can compare like all the requests made on version 2 against 3 or something.
Yeah. And the way this is this query isn't taking 7 seconds.
There's a little setup.
It's just running enough that they're saying that in the last 30 minutes we've spent 7 seconds in this one query. So
Is it analyzing a MySQL log file or something, or
this one,
does it have hooks in? Performance hooks into the MySQL?
I don't know how it works under the hood. I believe that this PHP version is like interfacing with. No, I think we put it on our database server, and it's like combining it. Maybe I have to. I don't. There's different ways to set it up. I think the PHP one actually hooks into the PHP.
Something. Your users are running the queries. This is actually just...
Or
just
our code is running the queries. This just kind of like peels back opens up the hood and just watches everything go and times it.
It's probably something like what you're saying.
Well, see, I'm not
Just a
familiar with
log.
what MySQL does. I know Postgres will log each query if it exceeds a certain amount of time to a separate log. And I would imagine that's what they siphon off and look at.
Yeah. No, this doesn't look at that because it's looking at the not slow queries as well.
Well, you can log all the queries, but typically I set a threshold. I want to know anything's taken way too long.
I don't think it's looking at the. I do not think it's looking at the database, especially because we have like many different read replicas out, so it would be hard for it to figure out. So. I think what it's looking at is the traffic, because it's pretty common how a program communicates with the database. Yeah. Mm-hmm. So I believe it's just looking at that go over the wire, and it knows. It sees like the SQL code come out, and then the response come back, and it says, okay, this is how long it took. Okay. Yeah, but even if you don't have this program, databases have slow query logs, or they just get to turn on profiling for everything, and then sort. And that, so at my first job, we didn't have this. I don't think this was invented yet. And so we would, when something was slow, we would activate profiling, and then it would store every query in the time run, and then we would export that into its own database and query that to find like offenders. Mm-hmm. But yeah, every database, I would start with a slow query log. You just open it up, and it'll have like anything you see there probably needs to be addressed because usually the threshold is like 2 seconds or something. Mm-hmm. Yeah.
So the other day you said avoid nested subqueries. So the other day I went through my code and I found something where it was doing a query in a for each loop. Right, so it was doing a separate database query every time.
That's even worse. Yeah, if you have a.
So I refactored that and turned it into a nested subquery. Did I make things better, worse, or stay the same?
Yeah, if you got a query out of a for loop, that's an improvement no matter what happened. Okay. But if instead of a nested subquery, if you could just join naturally, that would be good. I mean, we have queries. Sometimes you have to have subqueries. Sometimes you'll use like weird ORM software that generates really ugly SQL. And so we were having an issue with that. I had a situation where we had a I can't show you here, but we basically had like a subquery with a where clause, and the subquery had unions, and so it was like in this table get me everybody whose name is Aaron, in this table get me everybody whose name is Aaron, in this table get me. That's kind of what we were doing, but the way it was written was it was like select everyone from these 3 tables, and then give me everyone whose name is Aaron. And the hope was that the query optimizer would be smart enough to take that where clause and apply it to everything in the subquery, but it didn't. So what it did is it selected the entire database into a temporary table and then applied the filter. Yeah. So we had to have select everybody whose name is Aaron from this table, select everyone whose name is Aaron from this table, select everyone whose name is. It just you can get into trouble with subqueries.
But sometimes you have to.
And then subquery, MySQL will create a temporary table to work with it often to join. And if it gets too big, it's going to go to disk. It's going to just give up and go to disk. So sometimes people will do select where in and then a select, and if that select's returning 100 numbers or 10 numbers, it's not a huge deal. Other times people will do select where not exists select star, and that's bad.
Sometimes you have to do it.
No, in that case you could left join and then filter to where the join is null. There's ways to get around it. Yeah, so avoid subqueries unless they're tiny, unless they're really small. It's the more specific. Yeah.
Well, when it applies to what I do as a book indexer, you have main headings and you have subheadings, and you don't look under the subheading, you look under the main heading. You can't find where the subheading is unless you go to the main heading.
Oh, yeah, so that's kind of like a compound index.
It's the same principle.
Yeah.
Interesting.
So in what you're doing now, how many tables are there in what you're doing in your current job?
It depends. At one company I worked at, we would create tables just to do intermediate calculations. So we had thousands of tables. At this company, maybe we have a couple hundred tables. But then we also have document stores like MongoDB or something else that are just 8 tables. They have a lot of nested items.
Is that that's not a large amount of tables?
It's It's all relative. You can have applications that have like 5 tables. You have applications that have 500. As far as if that's good or bad, it really depends on the application. It might be like if you just have a few tables, that's not necessarily a badge of honor. It might mean that you have poor table design. Yeah. And if you have 1 million tables, that might not necessarily be a badge of honor either. So
it seems like people create like tables that connect to other tables together just out of habit. Like they may not
They
even.
make joint tables.
Yeah, but like they just put the references in those 2 tables that one table's joint.
yeah,
if 2
tables.
But you see that all the time.
If 2 tables have the same, they have the same exact primary key, and they probably, at least relationally, should be in the same table. But you might want to split them out because of the actual row size. Like there's optimization considerations there too. But if I had a table that was like employee number first name, and then another table that was like employee number last name, really that should just be employee number first name last name. But if I had if I wanted to have resume or something big or like a photo of them storing, like then I might want to split out to its own table.
Yeah, especially if you don't look at the things in the other table very often.
Yeah, the blob things.
For some reason. Yeah.
I
It's not
thought
so
that.
if you look
Or
at
if
it
you have a
very often.
one-to-many relationship, then you definitely want 2 tables.
And it gets complicated. Sometimes you might, MySQL encourages like normalizing, but sometimes you might want to like denormalize on purpose just to speed up. The table design and schema design is the number of tables is not like the best
Okay,
metric.
I just, all the stuff I've worked on, it's all kind of prototype level, and I've never worked on anything that had more than 20 tables.
Yeah, no, you can easily get to the hundreds of tables, like permanent tables, and then if you're creating temporary computational tables, you can get to the thousands.
Okay.
And some companies will make a different table for each like client. Sometimes make a different database for each client.
So say I want to index all the musical artists. So I have all the artists in the artist table, and all the albums in the albums table, and I need to have a multiple link between them because an artist will have multiple albums.
Right.
So you create a referential table in between that
You could, in that case, you could just have a table that's artist and album. Yeah. If you have, you would. Yeah, you would have like a table of albums. Although, since an album can't be shared by more than one artist, you don't need that intermediate table.
So you don't need the intermediate table.
Or actually, it could be. Yeah. Okay. Yeah. Sorry, an album could be shared. So yeah, it has to do with like if you're like a one-to-many or many-to-many.
Right.
The intermediate table is most commonly done for many to many.
It also depends on what you mean by artist, right? Like, are you talking about an individual or the name, the bands? Because the band can be multiple.
Yeah,
people, right?
it's
No, the band name. I should have said band. The band,
in that case,
not the artist.
I guess there are sometimes 2 bands collaborating,
If you have multiple
Or they
bands
get
on
into
the
a
but it would be less of a problem.
yeah, you could.
Okay.
Yeah, but that's
Oh, just use iTunes.
Could you go back a couple of slides?
yeah.
You had like these best practices, this list of best practices.
Yeah.
So I think that it was the 3rd one. And I think that the broader, the governing principle of that would be just don't prematurely optimize, right?
Yeah. I would.
That's a big problem oftentimes, like where you just like you foresee these problems that you really don't have any reason to think will exist in the future. Like
And that's what happened here. It was just like indexing everything. It was like, oh, maybe we'll want to query by old plan, which we never do.
So that's where things get overly complicated.
Yeah.
Just keep it simple until you need to. So like if the query is fast, but even without adding a secondary index or a compound index, if it's just fast, either way, and you could eke out more performance, it's like, why do it until it's actually a problem, right?
Yeah, well, if you can anticipate it's scaling, you know how it's going to be queried, then you want to add the index.
Yeah, in that case, yeah.
If you just know this is how it's going to be queried.
My only point is that's not always true. Like,
You should just go adding indexes willy-nilly is like the main takeaway. But sometimes you
I was just trying to
It's also
grab
dynamic
onto that recommendation you made.
that you have to pay attention. If you did a switch from an old plan to a new plan, you might want to have that index for a while. While you're working back and forth, customer queries.
if someone asks
after
like,
a few months, you can get rid of that.
What's
Yeah,
the
you
difference between those plans?
so typically you index the table for the way your application interacts with it, and then if you have like weird other queries, you would bring this data. You would somehow bring this data somewhere else that you could play with it. So we bring all of our data from various MySQL databases to Amazon Redshift, which is really good at like crunching tons of numbers. And so that's where we kind of just query like in weird ways is an entirely different database. Because what you want to avoid doing is coming up with a question, thinking like, well, I wonder this. And even if you create the index on large tables, that could take a minute or two or half an hour. And then so you create it, and then you just blocked production for half an hour, when you lose a ton of money.
Oh yeah, I actually had a question there. So you mentioned something like some technique to avoid that problem. Well, but I couldn't remember if you were saying just like run the query to different.
Oh yeah, no. So if you're gonna go mess around,
or something?
if you're gonna run selects, you can do this at a query level, you do it at a session level, but you can say, MySQL calls it a transaction isolation level. But here you're basically saying, I'm okay reading uncommitted data. I'm okay reading dirty data. And then this will make reads non-blocking. So there's times where I am querying production, so I always do this. And that way, if I'm doing like a huge long query, if you don't have this, if you're doing a huge long query and MySQL is trying to change the data while you're in the middle of like aggregating and adding things up, it's gonna block those writes. And then if you're saying like I don't care if I get new or old data, then it's gonna just allow the writes to go through, and whenever your read gets to that row, you'll get like whatever, like, it'll be old or new, like you don't sell.
I see.
So it's not exact. You can use this hint here.
Oh, that's cool.
Most MySQL companies still don't know about this, so I'm like always trying to sneak it in to let them know. Not that we encourage like raw querying our production databases.
I haven't used any of that.
Yeah, and there's like 4 different transaction isolation levels too. So there's you can get. But that's beyond indexes. This is I was trying to avoid like MySQL optimization in general because that's a really, really huge.
And that only applies in the context of the current query, right? Not like.
You can just if I run this here, I'll set it for my session. But you can have one query be like okay with 30 reads. You can just put it in the select. I'm not sure you can do that in MySQL, maybe, but
So your session being like your connection that it is?
Yeah, your connection.
Yeah, which would be okay if you're just like, analyzing.
Yeah. I mean, you could change the database and just like make that the default.
Yeah.
I wouldn't recommend it if you're doing anything that has to do with money.
Yeah.
Would recommend it.
But there's other things like if you have like a database you're just putting logs or something else, like then you can say writes. Like MySQL also try to preserve the order of writes. You can say I don't care about that. Like if 2 writes come in, like I don't necessarily need the latest and greatest. There's different ways you can kind of speed things up. There.
I didn't know that those were even options in SQL. Like I just thought you just had to deal with the fact that, you're basically saying you can tell it to be eventually consistent, right? As far as
well, like one use case for us is like if we want to compute the number of downloads for each video, so we show like this video has been downloaded 100 times. So then every night we're aggregating for every video how many downloads has happened, ever. We got smarter. We like stored last night's calculation, but like for a while we weren't smart and we just had this like query run on millions of rows. And the reason we were okay with that is because it only took like a minute and a half. So we're like, whatever, we can do it. But it was annoying because whenever it ran, then our application would time out. We had all these errors. Like every night at 10:06, we would get like all these deadlocks. And so just by saying like just read dirty, like if someone downloads something new, like we'll miss that and we'll say this has $200 instead of 201. But like we're not like billing someone's credit card twice or something. So there's situations you can
sort of looking at general numbers, maybe.
Yeah, if you're just trying to get like generals
exact
or like
thing
magnitude.
doesn't really matter.
Yeah.
Management reporting.
So how do you horizontally scale MySQL?
If you're trying to scale writes, if you're using the latest version of MySQL, you can create a cluster.
It is single master, multiple read clusters.
It's I'm not exactly sure the topology. I have not horizontally scaled MySQL. So you might know more about it than I do.
Well, I've never
In
tried
the-
it either.
Yeah,
So
no,
to
I-
scale reading, you can create read replicas,
Mhm.
and there will be delays between some of them, so you have to account for that. So we use a read replica right now. So for anything that's not a write, we actually read from the secondary, and unless it needs to like be within half a second of current. So if we're going to write something and then read back something, we're going to say we want you to read from the master, because whatever we just wrote probably won't have
The propagated.
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 But if we're just reading, like if we're just searching, just only read from the read replica. But that won't help if you write, because if everyone's trying to write, it's all going to go to the write master. So you can have so one way is partitioning a table, which essentially divides a table into mini tables. And so it's like, all right, everyone whose name starts with an A is in like this partition, everyone's name starts with a B is in this partition. So then if you're writing to B, it's only going to lock B.
So it takes a lot, like a concerted effort on behalf of the DBA, right? To really think through like how to organize the data. It's not just
To scale MySQL horizontally is difficult, which is why all these other databases were created. And it's relatively new.
Like Rethink, for example, it handles all of that for you. It just like you just set up nodes and it just starts distributing data.
Yeah, and it was created because
depending on the queries that hit each node, it'll optimize automatically for you.
Yeah, because it's probably sharding the data. It's like partitioning across, and it gets. Yeah, typically what we've done is just buy a better server. It's like Moore's law has been like way cheaper than like. To do all that, we'd have to hire like 3 people just to manage your databases. And for that,
sounds like a very challenging problem.
So you can, yeah.
I've heard people
and
say,
I even worked at my company that analyzed like economic data. And we had billion-row tables back, in early 2000. We were still just like right when it started slowing down, we're like, oh man, this is like I have to figure this out. And then like some new server would come out with 64 cores and like 128 gigabytes of RAM, which back then, even now that's a lot, but back then it was like infinity. And yeah, so it's I'm not. There's horizontal scaling SQL is possible, but it's not the best database for horizontal
it's more
scaling.
of like a DevOps DBA problem, right?
Yeah,
So,
but there's clustering. So MySQL clustering is the way you scale horizontally. But we just throw more money at it.
yeah.
All right.
So cool. Is that it?
That's all I have. Yeah. But don't throw more money at slow queries. Like, use your index right.
Yeah.
I was just going to say, I spent 20 years teaching that that wouldn't work.
Yeah.
I believe you.
Yeah, you throw the money at it once once everything's right. And it
But
really
yeah,
is just.
you don't want to. I mean,
That's
Well,
if you have an exponential problem, it's not
that was an excellent presentation.
Thanks.
good.
Yeah.
It was. That's great.
Round of applause.
All right. Well, thanks, guys.
I learned a lot from that. It's great.
It was real.
Yeah, and it's really clear. It shows a relationship. I mean, you talk about a reference interview. That's what you're doing. You're doing queries. It goes back to what we had to learn in library school. Is you got to make sure you know what the person wants. So you're not gonna,
Yeah. I mean, it's called indexing.
Yeah.
And indexes have been around a lot longer than.
yeah, what we say, it's in this
Databases.
article right here. 13 before books
Yeah.
printed. It's
Oh, file cabinet.
it's a this.
Rolodex.
Well, I showed this to some of you, but tomorrow is
Yeah.
National Indexing Day in Great Britain.
Oh,
First
really?
time
Oh.
they've ever had it. It's the 60th anniversary of the Society of Indexers. That's the UK version. We have American Society of Indexing. And
Is this library science specifically? Or
this is indexing. This is
Is it
indexing.
bigger than that?
Well, this is indexing books, database. I mean, it could be indexing databases. So we're indexing databases, not the same way that
Yeah.
we're talking about here. But it does tell you here, I'm sure I read it here, that, well, when I find it, I'll let you know.
It's not indexed.
No, when the first one, it was something like the 13th century. They were doing some stuff before the book was even, the printed book was even invented by
That would be
Gutenberg,
at Oxford then.
which is 1452. I can tell you
Before,
that.
before spelling was standardized.
Yeah.
Oh, well,
You should have
yeah.
come to the last
Now
meetup.
it's not standardized anymore. Now it's going the opposite direction.
So Craig mentioned that like the term we used for PCs, computers, you know, it was actually, they used to be a person. That was a job. You know, they were a computer, and they just like ran calculations.
Well,
in their head.
did you see
Well,
the
that-
Hidden Figures?
Yeah, there's
Hidden Figures?
on the screensaver.
No, none of you saw Hidden Figures?
I haven't seen it. Yeah, I heard about it. Though.
Yeah, it's the whole core of black women that were the computers for NASA. NASA would not have gone. John Glenn would not have gone out in space if it hadn't been for these women. And there's one woman when she was 6 years old. She was doing this math, and they got her, even though she was in the South and normally wouldn't have gone anywhere.
Yeah, in
they
those
got her into a
days.
school where she was able to learn all this. She was doing calculus, and she was 7 years old or something. And they had her, and it's pretty well based on John Glenn. And he was the one that kind of reached out because when the astronauts came to meet the people at Langley, where they worked, they had all these black women down at the end of the reception line, sort of, and most of the astronauts just kind of
Gone by.
dropped off. But John Glenn came all the way down and talked to each one of them, and then she came in. He wanted her to check the data. He wasn't going to go up until she checked out this data. So it's pretty amazing, and they were. And then one of them became the first black woman, and she had to get into the segregated code to go to the school to get her degree, computer engineer. Yeah.
I just wanted to say that, I mean, I bet a lot of the techniques that we use for like indexing databases and just the high level concepts there probably owe it to what we've learned in the recent and distant past.
Yeah.
Organizing
Amazed
information.
that we're still doing SQL.
Here it is.
So Aaron, I have a question for you.
I mean, that
Yeah.
today we can
Aaron.
have a
Oh
talk that
yeah.
I
So
still
connect back up there.
It's in a language I know.
What about whatever happened to query by
I
example?
should give it.
Is that what is that?
Query by example was a very early
I shockingly still
relational
remember a lot of
database
it.
access language.
Do something
That's
on
what they came up with before they came up with SQL.
I used to.
It was an old something that
QBE.
IBM back in the QBE back in the 80s
Oh, yeah.
at IBM.
So can you run over to your website and demo that?
Demo.
Demo your company.
Oh yeah.
Say I wanted to subscribe and I want to look up vintage electronics.
Yeah. Well, you can.
Clever of you to figure out how to get him to
Do your work.
So you can search without subscribing.
Oh, that's cool.
And so we don't have a
That
whole.
query was kind of fast.
Well, that's fast.
Yeah.
That uses
What kind of?
our search is actually powered by Elasticsearch, which is a different technology than MySQL. But it's
I want to see a Tesla coil.
there's you would query, and then if you try to download, it's going to say, hey, you need to pay.
Cool.
Now that query is doing more than just an exact match. You're interpreting things around vintage and around electronics to get images that were described a little bit differently, but still fit.
Yeah, it's full text indexing is another. It's a whole. We have like a guy who's the closest thing we have to a mad scientist who works on our search indexing. So I can't even do it justice.
Because that's the real value add, is being able to find the image you want.
Exactly.
Yeah, and sometimes you don't know what you want. So when you search for something,
Yeah.
Browsing.
so you
and
need to
that's
show
one
like
of-
related images.
And that's a huge field.
That's
That's where you
one of
get
the
the machine.
problems with
Having
having
instances.
So
having
puppy,
so
we have
much
like
that
kind of
you can't
related
browse.
information. Maybe you want kitties. Amazon does it with customers who bought this also bought this or
Yeah.
suggested. So a lot of times when people are looking, they don't have something sometimes they have something very specific in mind, and sometimes they just have like a general idea.
Yeah.
And sometimes they do
Music's
a great
even more
job.
complicated.
Sometimes they do a great job, and sometimes they're Amazon that keeps recommending you buy the same thing you already bought.
Yeah.
A lot of repeat buyers. So yeah, with audio it's even tougher.
Oh yeah.
And sometimes the library puts a book in that you thought should be here, and it's
You
over
can kind of-
somewhere else.
Yeah.
So Aaron, can you explain exactly what this is? So like I remember you explaining it to me, and you said basically like people who want to make like people who make YouTube videos, for example, and they just need snippets of videos. They can legally use that video.
Yeah, so if you're a news company and you're talking about something that's happening, this is just one example in Washington, D.C., you're not going to fly someone to D.C. to film the White House for like 30 seconds as like an intro to your story. Yeah. You're just going to
pick up some stock footage.
You're just gonna buy it. And so typically you would pay per clip, but with us you just pay one flat fee per year and you can just download whatever you want.
Oh, wow.
And if you sell it, you probably have to pay some royalty or something.
No, you could use it royalty free. It just has to be a derivative work. So you can't just turn around and sell it to other people.
Right.
So you use it in something that you create, you can sell that. So a lot of advertisers use it. We have a lot of like templates, I guess. Like if you have a YouTube channel or you're just making, you can have if you want like an intro, and you would put in your own photos and videos here, but just kind of like templates to create like logos and stuff. So it helps make people make their content. It makes their content look more professional.
Yeah.
And then if you need audio, like if you're a lot of videos have, you would then
hit the blues today.
look at that bug.
Oh, I see your
Yeah.
it's on there.
It's not good.
Bug report.
I know. They'll file that. Blues.
The speaker on that thing is horrible. That probably wasn't a bug.
No telling.
No, the bug is that when you mouse over it, it grows and kicks out the item below it. Yeah, there's a lot of bugs, but we're working on it. This site, our audio site gets the least load. It's a JavaScript problem. So, yeah, we have a large team now. But if you type in something that doesn't exist, I still leave my fingerprints over this.
Yeah.
Somewhere. Like, there's my puppy.
Oh.
It's our 404 page and error page. So I still try to sneak in. She's a lot bigger now.
I was just gonna say that she's really fucking.
It's actually really bad. So we were making the error page, and I was like, "We should put something here. How about a picture of my puppy?" And I thought we'd change it later, but of course the programming, you never change it. And so now my dog's name is Sophie, and that's become the lexicon for an error, either for a lost. It's also error. So people will be like, "Yeah, I searched for this and I got a Sophie." That's what someone will say. I tried to sign up and got a Sophie instead of hit an error.
Here it is. Records from the papal court at Avignon show that by the early 1300s, people were being paid to compose indexes. In other words, the professional indexer has been around for a good century longer than the printed book.
Yeah, that's cool.
In Avignon.
In Avignon, yeah.
All right. Well, thanks for listening.
Yep.
The sample data set is free. I just downloaded a PDF, so I can go ahead and post it. So if you wanted a copy of the presentation,
That's fun.
Okay.
Yeah, we'll include it on the GitHub.
yeah. All right. Thanks, guys.
All right, well, thank you, Aaron.
Yeah, it's my pleasure. I love talking about databases.
I could actually relate to it.